Our short code, our experiment today, I put the short code in the code folder in Microsoft Teams, and you can look at folder 03 multi-threading. Here we have only 3 files here: 01 race condition.c, 02 openmp.c, and 03 basic semaphore.c. You can download them all. So we are going to do the experiment on 3 files here. And we have a small task for you today, because when we finish doing some experiment here, I will give you a task to modify the code so that you can solve the problem of, for example, in the code number 01 race condition here. And do you see the result, what happened in there? And I would like to ask you to solve the race condition in the first example. And for the second file, you have the 02 openmp.c, this one. The example is very simple and show you how to do the implicit thread. It depends on your machine. If you assign your virtual machine to run on, let's say, 4-core processor, OpenMP will create a 4-thread for you. But my task that I ask you to do is that we can redo our assignment number. I believe that the assignment number 8 that asking you about the threads. You create many threads. Let's say in this case, I asking you to create 4 threads, and all the threads can help each other to calculate the summation. Let's say if I provide the input n, for example, if n is equal to 10, and if you have 4 threads, maybe the thread number 1 can calculate 1 plus 2 plus 3. Thread number 2 can calculate 4 plus 3 4 plus 5 plus 6. And thread number 3 can calculate, let's say, 7 plus 8. And the last thread can calculate the sum of 9 plus 10, something like that. And the main thread can sum them all and show the result. That is the task that I'm asking you to do. And the last one is just I would like you to get used to the basic API about semaphore. Before doing the task, I will show you how to run all the program and what is going on in each program here. Okay, so now when you're ready, starting your virtual machine, just let me know so that we can do the demo together. How about I give you just 5 more minutes so that you can get everything ready, and then we can start our program together. Or maybe while you are preparing your virtual machine, I can explain the code, what is going on inside the code that we are going to do. How about that? Maybe I have to put on my glasses so that I can see what the response from you. Right now, I would like you all to start your virtual machine and download the program. the sample program that I put it on Microsoft Teams. I believe that you can access Microsoft Teams from Linux as well, right? For example, I can access Microsoft Teams from the browser. I can use any web browser to go to the Microsoft Teams and download the file. You can download all three files here and put it somewhere in your Linux machine, in Linux VM. In my case, I put them in my document folder. Okay, I will wait for 5 more minutes and then we will start. Okay, I will start from the file number 1 first. You can use any text editor to open this file. In my case, I'm using the Visual Studio Code, but it's up to you. You can use any text editor. Let's see what is going on in this file. Before running the file, I think that it's better if you try to understand what is going on inside, and then you try to expect what the output is. When you try to think what is going on inside and you expect the result, and you can compare the result of the program with what you think. Let's have a look. The line number 4 to line number 9, they are just directives, right? We just declare how to find the API that we wanting to use. For example, pthread, semaphore, studio.h, and standard-library.h. Not studio, standard.io, sorry. standard.io.h. And then we define an iter, let's say about 1,000,000. And then we define in line 11, we just declare a global variable CNT, or you can change it as the calendar. In our lecture, we call it calendar. Let's think about the chapter that we discussed about thread and resting condition. And this file is the resting condition, rest condition. We try to simulate the rest condition. Look at line number 13 to line number 22. This is a function count, and it is a void pointer function. And it takes one argument, A, as a void pointer. This is this kind of notation is a bit different from other high-level programming languages, because in C programming, you can have void pointer function, you can have a void pointer variable as well. And you can expect that when you use the void pointer, you may expect that you will get a sort of address reference or something like that in this kind of argument. It is not the character, it is not the integer, it is not double. So what is it, right? You may have some kind of, you may have a question like this. What is it? It is not integer, it's not double, it is not a string. The void pointer, most of the time we use it as the address, reference to some sort of address in the memory. But we can use it for something else as well, okay? Here inside this function, we define variable I and TMP. Variable I is just for counting in the for loop, so it's nothing much here. And we count we start I from 0 until n equal -1, right? This is a very simple for loop. And what is going on in this loop? We just read CNG, we just read the value of carrier and assign it to TMP. And TMP, this variable is the local variable, while whereas a CNG is a global variable. And we update TMP by 1, and then we just store TMP back to CNT. This is quite similar to what we discussed in our lecture. We simulate that this function is a kind of non-atomic function that the objective of this function, we would like to add CNT by 1 every time we run the loop. But instead of using the instruction like CNT ++, now we separate the instruction into 3 instructions like this. And what is going on what will happen if this function will run in a thread? Let's see in the main function. In main function, we define TID1 and TID2 as a pthread T. We would like to get the thread ID. We would like to store the thread ID in TID1 and TID2. And we create a thread. Here is how we use the pthread create. We create a thread. And then we have to provide the TID1. And as you notice here, we have the ampersand symbol. When you have the ampersand symbol, I ever told you before that this is a kind of notation in C programming. It's some kind of look like this. It looks like an assignment operator as well in some cases. In some cases, it looks like this. It looks like we are trying to modify T1 with something. In some other languages, we might have a function like this. We would like to assign something to TID1. That is why we use the technical pass by reference to the function. When we have the ampersand here in front of the name of in the name of the variable, meaning that we would like to pass the address of that variable to the function. If you remember yesterday, when we passed the address, what is going on? When we pass the address of this variable to the function, whatever defined in that function, if it changed, this variable will be changed as well, because it is the same memory address. So here, when we create a thread, we will get the thread ID, and we can get the thread ID in this variable, TID number 1. And what else? So if you would like to know what is the parameter that we have to pass to this function, how can we know that? How can we know what is the next one? Why we have to provide the null here? Why we have to put count there? And what is null here? How can you know that? Why this one is null? Or why this one is count? Why that one is null? You can search. You can use the terminal, and if you would like to know, you can use the command man and then followed by any function in C that you want to know. For example, pthread create. This is the manual. Whenever you use any C programming in Linux and you would like to know what is this function and what the parameter that you have to pass to this function, you can use the command like this: man space followed by function name. So you can see that here are the arguments that you have to provide to this function. So you have to provide the thread, the pointer thread, and the attribute, and the routine, start routine, or a function that you want that a thread to run. And the last one is the argument for the function. Oh. You can go through the description of this function if you like, or if this one is not enough, you can search on the internet how to use this kind of function. To get out from this manual, you just type Q, and then you can go back to the command line. Okay, this is the help that you can use anytime. So whenever you use the C function in Linux, you can get the help or the manual of that function. Okay, I go back to this one. So null here is the attribute. So now we don't provide any attribute to the thread. And next is count. What is this argument for? This is the name of the void function, right? In our case, our void function name count. This is the function. And here, when we create a thread and we provide the count as the argument here, meaning that when this thread is created, that thread will run this function. And the last argument here is null, meaning that we don't provide any argument to this function. And if we can successfully create a thread, it will return 0. So when it returns 0, this condition is false. We can say that the condition is false. So we don't run the code inside the if here. But when we when the system cannot create a thread, pthread create will return something else, not 0, maybe non-negative value. When non-negative value has been returned, the code will execute in this block. So it will it will show this message on the screen and exit the program. The same thing happened here. We would like to create a thread, another thread, and we assign that thread to TID number 2. And we also assign this thread to run the function count. So now we expect to run the function count in thread TID1 and in thread TID2. So what you expect the result from these two threads? The thread TID1 just run this function, right? Just run this count function, and it will do the loop for 1,000,000 times. When it do the loop repeatedly, 1,000,000 times, what happened to count to CNT? CNT plus 1 plus 1 plus 1 plus 1,000,000 times. So CNT should be 1,000,000, right? Should be 1,000,000. And the same thing happened to TID number 2, because TID number 2 also run this function as well. So TID number 2 will update the CNT by 1. And because CNT number 2 run this one 1 million times, so CNT should be updated to 2 million, right? 1 million by TID1 and another 1 million by TID2. So in total, CNT should be 2 million. Do you agree with me? When we see the code like this, we should expect what the result should be, right? That is the result that I expected. And what is next? Here we have the featured join. So the main thread will wait for thread TID1. And next is thread pthread join again for the TID number 2. So the main thread will wait for the TID for the thread TID number 2 as well. If something happened to the pthread join, it will return non-zero value, so it can print out the error. But if the main thread can wait for the pthread join, this function will return 0. So it will skip what inside the if, right? And the last thing here, this is in main thread, because thread TID1 and thread TID2 does not include this code, right? They just execute the function count. So this happened, this line number 55 until 58, it just happened in main thread. If CNT less than 2 times n eta, or let's say if CNT is less than 2 million, print something. But if it is not, just print another message. Let's try what happened. Okay. To compile the code, I provide you the instruction how to compile the code. And you may notice that we have the flag LP. You have to compile it with the LP thread. Oops. 01, sorry, not 00. Maybe I changed the number. Okay. GCC provide the short code in C, and then you can provide the option output -o, and then provide the output name, and then you can provide the flag, the compilation flag. In this case, we would like to use the thread, and then we can run 01. This happened. In my case, it says something like that, like this. Boom, CNT is something like this. 118, in my case, is not 2 million. It's 1 million something. How about in your case? How about the result from your machine? The output is quite similar to mine, but the number here is a bit different. Or you got 2 million on your screen. Can anyone explain what happened? Why we get the result like this? Why don't we get 2 million? In my case, I get only a million something here. Almost 2 million, but not 2 million. Oh, not almost. It's very far from 2 million, actually, in my case. We have two threads, TID1 and TID2. They are trying to update the CT, which is the global variable, so they can share CNT together. But what is going on there? This is the example of race condition, right? This is the example of race condition. It try to update CNT, but when one thread updating CNT maybe hasn't finished updating yet, but another thread read the CNT, right? You can notice this one. This is the reading the CNT in one thread, and maybe another thread trying to calculate the result here and try to update this one back to CNT. It can happen. So the question is, how can you solve this? If I ask you to solve this problem by, let's say that these three lines must not be modified. Actually, we can modify these three lines because these three lines we just trying to simulate the rest condition. If you change this three line to something else, the rest condition may be gone. But I would like you to keep these three lines like that. But try to use the mechanism that we discussed yesterday and try to eliminate the rest condition. Now you may not able to do that, but if you ever do the multi-thread programming before, you definitely you can do that. But if you not get used to the multi-thread programming, try to follow the experiment today until the last file, so that you will get you will get used to the semaphore, and you may know what the API that you are going to use to eliminate the rest condition here. Okay. Any question before we move to the next one? So your task, when we finish all three experiments, you will come back to this file and try to eliminate the rest condition here by using the semaphore maybe. And my requirement is just only keep these three lines as they are like this. You don't have, you should not change them, but you add something else in this function, okay? But now you can see the rest condition, right? What happened to the share to the global variable CNT? We expect to get the 2 million result. We expect to get the result as 2 million, but now I got only 1 million something, which is much less than what I expected. Let's move on to the next one. You will come back to the rest condition.c later. The second file I provided to you is the OpenMP. In last week, we discussed about the implicit thread, right? We can create a thread by using the OpenMP. Actually, there are many API that you can use. In this case, I provide you with the OpenMP. In line number 4, this is the OpenMP header file. You just include it into this program. And you can see the directive on line number 9, Pragma, OMP parallel. This is the directive instruct that in the block below, which is this one, will be run in parallel. And it depends on how many CPU cores that you have. In my case, I have 6 cores in my machine. So I expect to have 6 of these messages. I expect to have, this is a parallel section 6 times. I expect to have this 6 lines. And here in line number 15, this is not in the pragma. It is not in the block above. You can notice that we can define the block by using the curly bracket, right? So here, it is not in the block, so this code will run sequentially. So when we expect something like this, let's try what happened in the code like that. Okay, and you may notice the command that we use to compile the file is very similar pattern to what we use in compiling the pthread. But here, we just use the flag OpenMP there. Okay, I try this one. Okay, successfully compile. And then when I run 02, okay, I can get 6 of parallel section 1, 2, 3, 4, 5, and then 6. And then I get 6 of the thread number 0, 1, 3, 5, 2, 4. And the last one is, this is from a sequential section. So it is the same as what we expected, right? How about your output? If you set your VM to run on just only one single core, on single core, it will have, you will create the program will create just only one thread, one additional thread. But if you set your VM to run on more than one core, let's say 2 or 3 or 4 cores, you will get a message like this. You will get messages like this. This is the OpenMP. Who can get the message similar to this? Who else? Maybe you're sitting too far, I cannot see. Sorry, I didn't get you at the very beginning. How? It depends on how many CPU cores you assign to your virtual machine. In my case, I have 6 CPU cores for my virtual machine. That is why I have 6 threads. When I have 6 threads, the system will create 6 threads to run in the code in this block. Then I have 6 threads. So this block will run 6 times. Not 6 times, it's 6, but by using 6 threads to run this block. Okay. So the thread number 0 run this instruction, and then the thread number 0 run this statement again. But when the thread number 0 run this instruction, it will call this function as well. OMP get thread num, and it will return 0 for thread number 0. That is why I got the result like this. But you may notice that thread number 1 may not follow thread number 0, or let's say here, thread number 4 is the last one. Thread number 5 might not be the last thread in my case, because I have 6 threads from 0 to 5. It is not necessary that thread number 5 going to be the last one. It's not, right? You can see the result here. And this is just lucky me that I have this and followed by that and followed by this, but it is not necessarily like this. I can run it again, and the result may be different from what you can see. I can run it again, and you notice that the result here is different from the above. Because in multi-threading, it is not the sequential programming, so each thread can run, and it depends on the process dispatcher to manage that thread to be executed by the CPU. So the thread number 0 may be the first one, and then followed by thread number 5 and later. You may notice that here. This is a parallel session, 2 messages followed by each other. They are different from this one, right? This happened in multi-threading. If I run it again, you may see the different result. I expect to have the different one from the previous result. I can run it again. At this time, I get 0, 1, 3, 4, 2, and then 5. And I have this message. This is a parallel section alternatively with the thread number, right? But it is not necessary to have the sequence like that. Okay, you can see the different result can happen. You may notice something like this. If you would like to try, you can assign more CPU cores to your virtual machine. You can try. How can you set more CPU core to your virtual machine? You go to setting, but now my virtual machine is running, so you cannot change it straight away. You have to shut it down first, and then you go to the setting, and in the system, the number of processor here, you can specify the number of processor here. In my case, I'm using 6 CPU, 6 processors. So if you would like to try something like this, you have to shut down your virtual machine first, and then come back to this setting, and then you change the number here, and then you restart your virtual machine so that you can see the differences. Any question of the second example? What do you think about the OpenMP? Is that easy? Is that, or what do you think about the OpenMP? Not thinking in anything? For me, I believe that OpenMP is quite easy, but there are some limitations. But I didn't discuss the uh, limitation of OpenMP here. If you would like to study more in OpenMP, you can try it by yourself, and definitely, the more you study in OpenMP, the more you will know about it. Okay, but in general, I believe that at least now you know what the OpenMP is, and now you know how to create threads by using OpenMP. In case that you have more than one processor assigned to your um, virtual machine, as I said, you expect to have something like this. In my case, I have 6 CPU, 6 processor, so I got 6 threads. If you go back to the assignment number 8, asking you about the summation, I ask you to, let's say, create two threads. One thread calculate the summation of the first half, right? And the second thread calculate the summation of the second half of n. Let's say if n equal to 100, the first thread calculate the summation of 1 plus 2 plus 3 until 50. And the second thread calculate the 51 plus 52 plus until plus 100. And finally, the main thread can get the result from both two threads and sum them up together. That is one approach. The task that I would like to ask you to do today, just stick with the assignment number 8. But how about trying to implement it by using OpenMP? Can you do that today? We are creating at least 2 threads. It depends on your machine, right? If you assign only 2 processors to your VM, you have two threads. If you assign, like my virtual machine, I have 6 processors. I can create up to 6 threads. Can you use the OpenMP to do the same as what you asked in assignment number 8? You will spend your time to do it today, right? Okay. Any question of the task for today? And you will. I believe that you may spend some time to do it. And if you need help, just let me know. But now we are going to move to file number 3. Any question before we switch to file number 3? The example that I provided here, OpenMP get a thread num, can help you to distinguish the thread number, right? You can use the simple if else to identify which thread you're working on. So if you're working on thread number 0, what do you want to do in thread number 0? If this one return 1, right? If OMP get thread num return 1, what you want to do in thread number 1? So you can use this function to separate the task in each thread. Okay, let's move on. Sample number 3. This sample number 3 is very simple. It is the example how to use semaphore. This is the one we discussed in our lecture yesterday. Let's have a look. The difference here, we just have a directive include semaphore here. And look at line number 6. Line number 6, we define mutex as a semaphore. You can use any name here. You can use any name here. You can name it A, you can name it B, whatever you like. In this case, we just name it mutex as the semaphore type, okay? Semaphore underscore T. And then look at this. I will look at the main function first. So in line number 25 until 35, it is the main function. In line 27, there is a function semaphore in it, and then followed by mutex, and then followed by 0, and then 1. May I ask what the 0 mean and what the 1 here means? Can anyone answer me? If you don't know, how can you know it? How can you find the details of this? You can use the internet, or you can go to the command line and then man, and then semaphore in it, right? You can go online, you can search from the internet, and I believe that many of you, if you got the question like this, you will go straight to the browser. Even myself, sometimes I go straight away to the browser. But as you know that if you would like to do some programming in C, you can ask the system, and the system can show you. Okay, the first argument is the semaphore, and the second argument is p-share, and the third argument is the value. And what are they? The p-share argument indicates whether this semaphore is to be shared between threads of a process or between processes. So if the p-share is 0, the semaphore is shared between threads of a process. If p-share is not 0, meaning that semaphore will be shared among processes. So it depends on whether you want to use the metaphor for the processes or between the threads. So in our case, p-share is 0. That means we are working on the semaphore for the threads. Okay. And how about the value here? The value is the initial value of the semaphore. So here, instruction in line number 27, meaning that we would like to initialize the mutex semaphore, and we will use this mutex semaphore between our threads, and we initialize it to be 1. We assign it to 1 at the very beginning. And next, we have seen these two functions before, right? In the rest condition, we use the pthread create before. So this is the same as before. So this is PID, but instead of using a PID, in this case, we define it as T1. And no attribute, and threads is the void function, right? This thread T1 will run on the function name thread. And how about the number 1 here, the string 1 here? The string 1 here is just the argument to thread function, right? So we can see the thread function is here. This is the thread function. The definition of the declaration of thread function is here. So T1 will run this function, and the number 1 here, the string 1 here, will pass to ART, and then we can use the casting to change ART from the void pointer to the pointer of character, or you can simply say that it is a string, because in many programming languages we have string, but in C programming we use the pointer of character as the string. And what happened in this thread function? In this thread function, we call semaphore wait, and followed by the semaphore name. And we do something here. We know that this is the instruction in this section can be the critical section, right? Whatever you're doing here, we can call it critical section. And finally, we can release, right? It's just like we acquire the lock and release the lock. So we use the function wait to acquire the lock, and we use the function semaphore post to release the lock or signal. In our lecture, we have wait and signal, but in POSIX API, we use wait and post. Okay. What does it mean here? We create the thread T1, and T1 will run this function. When T1 run this function, what happened? Definitely, the string number 1 here will be assigned to TAID, and then we call in line number 13, we call semaphore wait. So we lock the inside, right? We lock the inside. So T1 will do this one first. When T1 finish, when T1 doing this and that, line number 14, 17, and 20, then it release mutex. What happened to T2? T2 will run the code like this, the same. And because T1 locked the mutex, meaning that we expect to get the result from T1 first. When T1 finish, thread T2 will follow, right? And then we have this semaphore distort to release the semaphore. This is how we use semaphore. We use the semaphore init to create the semaphore, and we initialize the value of that semaphore. When we finish, we just destroy. So I'm going to compile and run this file. ECC 03. And just simply run it. Okay. In my case, thread number 2 run first. So when thread number 2 run first, it show the message enter TID number 2. T number 2 is in critical section and just existing TID number 2. And later, the thread number 1 can execute the thread function, the rest of the thread function. It depends. The thread number 1 can start first, or thread number 2 can start first. When I run it again, maybe thread number 1 can start first and thread number 2 later. But you notice that whenever the thread start, it locked the mutex. So it continue until it finish. In this case, thread number one start first. It continue until the mutex was released. So thread number 2 can continue. But in the first the first experiment, you can see that when the thread number 2 start first, it will lock the mutex. So thread number 1 cannot start. It had to wait, right? When the thread number 2 finish, the thread number 1 can start. You can use this kind of idea, this kind of concept. Try to use this semaphore, the API, and wait post function to solve the first task. Because in the first task, you see that the result is not correct because the race condition, right? But I ask you to keep these 3 lines like this. I ask you to keep these 3 lines like this, but add something else there. Actually, this is not the practical, it is not the practical, it's not the best way to do that. But I just want you to keep this, those 3 lines and add semaphore something there. Okay. Any question of the task for today? What are you going to do for the rest of the class? I asked you to do 2 things, right? First, edit the first file, the rest condition, so that the rest condition is no more. You can use some API in the example 3. You can use semaphore in it. You can use semaphore destroy. You can use semaphore wait and use semaphore post. You have to use them somewhere in file number 1 so that you can eliminate the race condition. And the second task, I asking you to implement the assignment H again, but instead of using what you used before, now I ask you to use the OpenMP to calculate the summation of n. And the number of threads, it depends on the processor that you assign to your virtual machine. Let's assign more than at least 2 processors for your virtual machine. If you assign 2, 4, 6, it's up to you. You can choose it by yourself. Any question? Okay, now I will stop my presentation now, and you can work on the task today. I stay here in case that you have any questions, just ask. And your TA are at the back of the room, so you can ask them as well, or you can ask me. And students on WebEx, if you have questions, just ask straight away. Okay, I will try to come back very soon.